Hello, everybody. Hello,
Hello,
Celso.
hello. How
How
are
are
you
you?
today? I'm good,
Good.
thank you.
So it looks very sunny in your stadium. So where are you? Currently in Australia or at home?
I'm at home. I feel at home in any place.
Okay, very cool. So thank you very much to all the people who just attend the training for today. So the topic for the webinar is measuring and tuning professional audio systems. And I'm very lucky to welcome you, Celso, with me. So you will be the panelist. So can you maybe introduce yourself, just that you know who you are? Celso, yeah. Can you hear
Ah,
me?
okay. Yes, you want I introduce myself. I'm
Yeah,
Celso
please.
Papadopoulos. I the sales manager for Europe for
Okay.
Nexo,
Yes.
and and I know a little bit about some tuning, and I try to understand. It's good I'm here because if I understand, everybody can understand the explanation. So it's a good point.
Yeah, that's a good point. Okay, so let me introduce myself. So I'm Nicolas Poitrenaud from Nexo Engineering Support. So I'm just part of the team who gives support to our customers all around the world. Very involved in the education program. And this is our first webinar just about measurement and tuning. So we did many webinars about acoustics and about, about system design, about system installation. And this is the very first that we did on tuning and measurements topics. This is something that we used to cover when we run our this was ETC, now it's called Audioversity, but this is something that we used to talk with the customers, but this is the very first time in the webinar. Celso, as you mentioned, you will be the panelist for today. So what does it mean? It means that we all have access to a question and answer window. So for people who would like to ask any questions, so feel free to write any things on these Q&A windows, and then Celso will be the guy who interrupts my speech and say, hey, can you make it more clear? Or can you explain? We have some people who would like to know about, and so on. So please feel free and use that Q&A. You also have a webinar chat. If you feel like discussing with you guys, feel free also to use that webinar. But for question and answer, it's better for us just to manage this Q&A window. So how will it happen for this webinar? So I will alternate between a presentation. So I have a PowerPoint presentation, but I will try also to manipulate any measurements with a measurement software. So we can try to do some experiments just by doing time alignment, or maybe try to understand what the basics, what is an impulse response, what is transfer functions, why should I use this display, and why shouldn't I use another one. So this is more or less like, understanding the basics, understanding just how to use properly measurement tools. So let me start with the presentation. So measuring and tuning professional audio system. We'll start with something which is a little bit provocative. It's about these quotes that say measurement is not about software learning, but it's about everything is about everything but the truth. So this is a little bit provocative, but what I want to emphasize here is just to say that this webinar is not dedicated to any measurement software. So I will use a measurement software to do the demonstration, but it's not about how to click on that menu and how to use properly any measurement software. The idea is just to understand how we can do a good measurement and how we can understand what we see on the software. Okay, this is probably the most difficult thing, is not to use the tool, is to understand what you do and to put that in the context. As I mentioned, as a support engineer, I used to travel in many places, and I saw many people using measurement tools for tuning the systems, and some of the people did absolutely great job. But what we realized also sometimes is that it was better before the tuning than after the tuning. Okay, And this is a problem, okay, because you have all these very sophisticated equipment with a computer, software, sound card, expensive microphone, but you don't really know what you do, what you are doing now. And sometimes it was better before they did the tuning. So the question is first about why do we measure? So why do we have to take sometimes our measurement tools? We have many answers that we can have to this question. The first one should be, for example, check our speakers in the warehouse. So if you want to check the speakers in the warehouse, this is probably the best, I would say the most efficient way of doing a measurement. The reasons is that you can repeat exactly the same measurement conditions. For example, if you are in the warehouse, you have your speakers, so you get the speakers for the very first time, you want to measure it. So you put the speakers on a pole stand, on the tables, you do the measurements and you keep the measurement as a reference. And maybe 2 or 3 months later, you come with the same speakers, do the same measurements. But what is good is that you keep exactly the same acoustic conditions. So it's very easy to compare. So check speakers in the warehouse is why we also sometimes have to measure. The second question is fine-tune frequency response on site. Okay, so this is currently what we do. So we install the system, so we put some in the system, and then we need to have measurement, objective measurement to fine-tune the system on site. We also need measurements to time align with other speakers. Okay, in that case, this is also very useful and very objective. So yes, we need that. We could also need to do measurements to control coverage consistency, but to be honest, between you and me, if I need to control coverage consistency, it's better just to play music in the system and to walk through the audience and use your ears just to control the coverage. It's much more easier to get the good idea of a coverage just by working through the audience instead of having a microphone. But anyway, if you want to measure, you can. Sometimes you also need to confirm commitments. So when we go, for example, into stadiums or sports arenas or anything, we had some sound pressure level requirements. We had also some speech intelligibility requirements. So we need to measure and just prove that what we sell to the customers is confirm the commitments that we get. So we need to measure. But again, sorry to be a little bit provocative, but sometimes we also measure just to show we are experts. Okay, so we can see many people, and I can share my experience of seeing many people having very sophisticated equipment, and they don't really use it properly, or they did very simple things like measuring RTA, for example. But what they wanted to prove is only that they were the expert of the tuning. So yeah, sometimes you get the measurement equipment just to show that you're an expert. Before we go more in depth and we explain what we can do with all this measurement system, I would like to go into introduction and fundamentals. So we need to know a little bit more about fundamentals. First, you never measure if you don't check your system before. Okay, so no measurement prior to full system check. The reason is this one. If a speaker is disconnected in a line array, okay, so it will change, all these line source criteria. So there is something which is wrong, that goes wrong into the system, but this is not real. This is not due to the system. It's just because there is a speaker cable that has not been checked. Sometimes you also have phase reverse, or sometimes you have a delay somewhere in the audio chain. So you never measure if you don't check your system before you fly it. So first, you check your system. Second rule is always trust your ears. Always trust your ears. Okay, more than any measurement. Measuring is something, okay, but you cannot avoid having your ears just to check what you're doing. just remember that when you go into a sound system is not, this is not a movie, this is not pictures, okay? This is dealing with your ear perceptions. So that's great just to have these very nice curves on displays. This is very helpful, but you must have something that sounds very great. So always trust your ears more than any measurement. And the good way just to trust your ears and to be honest with what you're doing is always question what you're measuring. Don't be, you must stay proactive, okay? When you go with your measurements, don't be passive, just like looking at your computer. You need to understand exactly what happens, okay? So you always have to question what you're measuring. Right, so let's have a quick overview about measurement tools. So we need measurements tools to get our measurements. So we need hardware and we need also software. And for hardware, what we need for sure is first we need a microphone, okay? So we are very lucky now because from the past, having a measurement microphone was extremely expensive. So we have a good example of this one. I don't know if you know this one, Celso, DPA, BNK. So BNK, so DPA is a branch of BNK, or it's more or less the same. So it's the same company. But these are measurement microphones which are extremely expensive. So it's more or less the same price as a studio microphone, something like 2,000, 3,000 euros for one microphone. So they are very good. Huh? They are a very good microphone. But to be honest, we don't need such big performance when you're on site, because when you're on site, where you're on the field, there are so many other parameters that can corrupt the measurements, that getting something less expensive. So we have this one. I think this one is something like 150 euros. So it's more affordable. You can buy also some of them for 100 euros. And they are just accurate enough to do measurements on site. So currently, you can buy this one. This is absolutely perfect. So you need a microphone. And you need maybe also a software. So what do you need as a software? So we have two different categories of software. We have the one, what we call mono-channel FFT measurements. So what we used to do is FFT measurements. So we have two categories. One is mono-channel. So we send like a sweep, okay? And we just need one channel for the microphone, and that's it. And we measure. But in that case, we need to use a signal that we know. So a signal that we know is most of the time a sweep, okay? Because we know exactly what happened with the sweep. And on the other category, we have other software that use what we call dual channel FFT measurements. So when we say dual channel FFT measurements, what we mentioned that we need two channels for measurement. The one is the microphone, and the other one is the reference, okay? And we will compare the measurement with the reference, okay? But the good points with the dual channel FFT is that we can use any kind of signals, okay? So it could be, most of the time the people use a peak noise, but you could use also music, okay? And this is why dual channel FFT measurement is really loved by the user, is because when they run the live show, they can use the mix of the consoles as a reference signals and keep on doing measurements in the show without playing any sweeps or any, peak noise or anything like that. Okay, so dual, yes.
Nicolas, could you explain FFT means, please?
So FFT, right, so FFT is fast Fourier transform. So Fourier transform, I will explain that later, is a calculation, is something which is done into the software that goes from the time analysis to frequency analysis. Okay, so this is what is FFT. So currently all the software that I show you now, they all do FFT calculation. This is the only thing that they know, that they can do. So we have many examples. So from time to time, we use this one. So we have Systune again. So not to do any promotion to any brand, because we are not manufacturers for any measurement system. So we have a lot. So this one, we have Systune. I think this one is also very used by many people. So Smart software is also a dual channel FFT measurement. But there are many other ones. So we have another example. Pure Analyzer Flux is a French company. We have some other which are expensive, some of the other are less expensive, some of the other are very cheap. But anyway, so we have a lot of very good software that can do the job. Anyway, Celso, you may know that sometimes you don't have your computer, okay? Yeah, but that's okay. If you don't have your computer, then having a tape meter is also good, okay? At the time we have to deal with, time alignment. For example, with Nexus speakers, we have something which is called phase linear. So all our speakers are compatible in phase, and they all take the same origin as the front grill of the speaker. So if I need to time align, I just have to take my tape meters and just calculate the difference between, for example, the main PA and the delay speakers, okay? And just get this time value inside the amplifier, okay? So tape meter is enough. From time to time, it's quite a big distance, you know, when you go into, stadiums or, arenas. So you need a big tape meter. So what we used to play is with a rangefinder, for example, or lasers, but it does exactly the same, okay? We just keep the measurement. So don't be afraid. If you don't have all these sophisticated computers or sound cards or microphone, just having a laser can save your life. Right, so let's carry on, and let's have a discussion about measurement fundamentals. So I will start with the explanation of how we can do any measurements. If you run dual A50 principle, so if you run dual A50, so fast Fourier transform, this is more or less what we use. So we have a computer with sound cards, and this computer is just generating signals. Okay, so it could be music, it could be noise. So most of the time, this is a big noise. Okay, and then we feed the systems with the reference generators, and then the loudspeakers just playing the sound and goes to our measurement microphones. Okay, and then we keep the measurement microphone and go into the input of the sound cards. And remember, as we do a dual E50, we will compare the measurement with a reference. Okay, so we need to do a look back like that and keep the reference and go to the second output. And then we compare measurements with signals. Then what do we display now on our software when we get this connection? So we have two different analyses, as I mentioned before. The first one is the frequency analysis. Okay, so what we used to visualize most of the time is what we call transfer functions. Okay, transfer functions is a mix of frequency on the x-axis and level on the y-axis. So this is for the magnitude. Okay, so this is frequency response. But transfer function is also the phase response. Okay, so if we have to talk about what is a transfer function, this is a combination of magnitude and phase. So magnitude response, so frequency response, sorry, and phase response. Okay, so we need both of the curves. But we also can display a time analysis. Okay, and what is a time analysis is most of the time what we call impulse response. Okay, what is impulse response? This is the response of the systems to a very short peak. Okay, so a very short peak in physics, we call that Dirac impulse. Okay, but it could be like if you clap your hands. Okay, it's more or less the same. So it's very short in time, and the energy is very high. Okay, so this is a perfect impulse. So we go in, we take the impulse into the systems and we get the impulse response. In reality, what is very useful is if I have a transfer functions, I can have impulse response at the same time. Okay, and how can I go from impulse to transfer? Just by doing fast Fourier transform. Okay, so I can play with both of these display. I can display everything at the same time, and as a user, it will be very useful for me. So you know what? Let's put that into practice and let's have a look together. So I will maybe share another part of my screen. So let's share, let's share my measurement software. Where is it? It's over there. Right. So I'm sure that you know this software, gentlemen. So this is a smart one. But again, for me, the idea is not to explain. There are many, tutorials. There are many things about how to use the software. So it could be another software. I don't. It could be, the Systune. They all do more or less the same. So currently, what I'm doing is I will just. So I don't have any speaker at home, Celso. I don't know if it's the case for you, but I have no subs. Yeah. So the only speakers I have is just for listening radio on my bathroom. So I don't have any very professional speakers just to do the measurements. But there is something that I have is I have a controller on my room. So currently this is so we stop sharing that screen and go. So can you see this is the back of my controller. So this is my desktop. So I think you can see me now. If I say hello, you can see me.
Yeah, hello. I see.
Okay, fantastic. So what I do, so what I'm trying to simulate is a behavior or speakers or anything, but I don't have any speakers. So the only thing I have is a controller. And the good point with a controller is I have filters, I have delays, I have level, I have many things. So what you see on the backside is the red cables. The red cable is the input, okay? And the black cables are the output. So there is output 1 and output 2. So output 1 could be, for example, a main speakers, and output 2 could be a delay speakers. Okay, so I can, get both of the outputs, have the delays, and change the level, whatever I want. But I can also use any crossover frequency, and for example, try to get a subwoofer on channel 1 and a passive speaker on channel 2, or maybe have active speakers with a low frequency driver on channel 1 and high frequency driver on channel 2. Okay, so I can do anything with that. So I use my smart just by generating a noise into these processors, and then I go with 2 outputs, and I can mix these processors. Okay, these outputs. So I have mixers, and then I can mix channel 1 and channel 2. Right. So what I'm going to do now is I'm going to just measure the processor with nothing. Okay. So a processor with nothing means no EQ, no delay, nothing. Okay, so let's do that. So go back to my smarts.
Nicolas.
Yes.
We are seeing the back. Thank you. We are seeing only the back of your.
Yeah. So this is the main screen. Good. And great. So what you see now is my systems. Okay. And this is currently what I see. So what I'd like to measure is only my box. So sorry, I will maybe go and just so that the people see my face. Okay, because sometimes I use, like that.
Good.
Great. So what we see currently is we have on the bottom part of the screen, we have a magnitude. In the middle, we have a phase. Okay. And on the top, we have impulse response. So what I should measuring now is an empty box. Okay, so if this empty box is perfect, and it should be the case, I should have something completely flat, and it's not completely flat, Celso, okay? So what is the reason for that? Why it's not completely flat? If you see on the top, what we can visualize here is what we have the impulse response, okay? And the impulse response comes 78 milliseconds after the measurements. Okay, do you have any idea, Celso, any idea why do we have so big delays when I do the measurements?
Because the signal measure and the signal generate should be arrived at the same time to be compared.
Yeah, absolutely. So they should arrive at the same time, but they don't arrive at the same time. So what could be the reason for that? Any idea?
the latency of the system.
Absolutely, you're right. Okay, thank you. 1 point for you. So this is the latency. So we have many latency because we have digital. So I have a sound card with the converters. I go to a second converter to go to the processing. I have another converter to go to the mixing desk and another converter. So there are so many converters at the end that we have something like a delays of 27 meters. Okay, so it's quite big. So why do I have a very so if I want to do a measurement currently, what I see is a big is something like it's a little bit messy. The phase is shaking. Frequency response is not very good. So one of the first priority when I have to do if I want to do a time alignment between measurement and reference. So we can do it just by clicking on find here. So we can see that I will do a time alignment. So this is 7.8 milliseconds. So, and as long as I insert, then you can see here that then I got a very flat trace and everything is great. Okay, so one of the basics when you do the measurement is always make sure that you have measurements and you have the reference that comes at the same time. Okay. So, and most of the time, I don't have any so much converters because if I measure loudspeakers, most of the time the delay will be due to the time propagation, okay, from the speaker to the microphone. So if my microphone is very far away from the speaker, then the delay will be also big. So I need to put the delay on the reference, okay? And this is what we did before. So what we visualize here is the arrival times of my measurement. So this is late. So in that case, we can see that the transfer function is affected. Okay, so it's shaking a lot, so I can do very accurate thing. And if I do now alignment with the signals, then I can go and see a beautiful trace. So I forget to mention, we have something also here, which is a red curve, which is called the coherence. So what is the coherence? Coherence is a trace that just show the users if the measurement is affected by nonlinearities or by noise or by any mistakes that comes from your measurements. And this red curve is absolutely essential when you use it because it tells a lot about what you're measuring. Are you good? Are you doing some mistakes? And well, so it's you really have to take care of this red curve. Okay. So just to come back, if you're in a room, most of the time when you're in the rooms, you have reverberation. So what does it mean? It means that you can have any reflections. So I can simulate reflections on the impulse just by adding a delays. So my signals will come to my mixers, and I just inserted a delays on the mixers, and I'm going to add a delays now on my analysis. So if I add one reflections, okay, so now you can see there is a comb filtering. Okay, thank you very much. And if I add now a second reflections, okay, so you can see now the second reflection that's coming here, okay, so you see the second one, so you see the current is going bad now. We can see that what we are measuring now is affected by our reflections. And again, if we go into the room, so in a room we have we have this reverberant field, which are very big. And if I just put the reverberation, so I have a reverberation in my mixer, and you can see that this is what you measure now, okay? So it's no more, remember we had this one, at the very beginning we have this one, okay? So it was perfect, this is my speakers in an anechoic room, but if I have everything now, this is what I get, okay? And I had to take a decision with that, okay? This is what is extremely difficult. I know how to run the subra, but I need to take any decision like that. So what I see is all these parts of my screen is affected. So at the very beginning is a comb filtering, so it's muchly affected by the reflections. And then we have this kind of shaking frequency response, and this is due to the reverberant field.
Nicholas.
Yeah.
In terms to understand, for example, all the reflection in the linear impulse response window, what is the relation between these different time reflections, frequency and phase?
So if we have, for example, 5 milliseconds, so if 5 milliseconds is equal to half of a period, then it goes to phase oppositions. Okay, so if I had to do any measurements, I had to divide 1 divided by 2 times 5 milliseconds. So it will be 1 divided by 10 milliseconds. Okay, so I think 1 divided by it should be 100. Okay, so we have the first here constellation is 100 here. Okay, and then this is every odd multiplier, so 300, 500. Okay, will be the constellation for the sound. Okay, so it could be a good clue if you see, for example, comb filtering, if you see the position of a microphone with a wall of anything, just by looking at the measurements, the space, and looking at the constellation, you can say, okay, this is due to a microphone or something like that. Okay.
Okay.
Okay, but as you can see also, sorry. Yes. So I need to go again. So as you can see here, we have our measurement system, but the delays also is affecting the phase. So what is important with this value is if, for example, my system is late. So you see now that my system is late because the impulse response is not synchronized. So when the system is late, you can see that the phase response is affected. Okay, and currently when you introduce latency in the system, then you can see that the slope of the phase is going negative. Okay, so as long as I need to use this phase trace to do alignment with subwoofer, I need to make sure that I 100% understand what I'm doing with these time alignment procedures. It means that if I put a delays, once the delay is set up, I mustn't change it, okay? Because if you change it, then you will just change the phase response, okay? So let's summarize this one on the different slide. So if the measurement is time aligned, then it's perfect. And what I show you, if the measure is late, then you create a negative slope, okay? If the measure is in advance, then you go to positive slope. Okay, so what we want to do is to get exactly a signal line. This is a little bit of theory just to make sure that you understand. The phase are related to the time, but also frequency. So a phase shift is equal to this formula, so 360 degrees multiplied by frequency multiplied by time. So what does it mean? It means that if I put 1 millisecond of delays, for example, this will be only 36 degrees at 100 hertz. Okay, so this is a phase shift, but it will be out of phase at 500 hertz. Okay, and then it will be in phase again at 1000 hertz. Okay, so for a fixed delay value, phase shift is always more important in the high frequency compared to the low frequency. And this is exactly what you see. So when you have to read a phase trace, this is what you read here. Okay, we have what we call a wrap phase representations. So we have a delays, for example. So the delays could be 1 millisecond, and you see that just implementing 1 millisecond of delays, we create a slopes. But once we get one cycle of phase shift, then we go back to the other value. Okay. So in that case, instead of using a very big screen going from 0 degree up to 360, 500 degrees, which is too big, what we prefer is going back to the initial cycle, okay, to the first cycle. And what you see here is a wrap phase representation. And every value here means that we get one cycle of phase, okay? So this is one cycle of phase rotation. From time to time, some people, they use what we call unwrap phase representation. And you see that on the y-axis, we have many information that goes to, you know, this is something like 600 degrees. So I can increase the windows very big. So delay and phase, once again, this is very important for us. When you consider phase measurement, time alignment, between measure and signal or reference signal, time alignment between measure signals and reference must be set very carefully. Okay, so you get the signal and you don't change it.
Okay.
Okay, so let's go back to a presentation. I try to not to do any mistakes now. So I will go there. So we talk about these fundamentals, and then I'd like to discuss now into practical things. I'd like to discuss about microphone positioning. Okay. Celso, can you confirm that you see my presentation now?
Yes, I see
Okay,
your
thank you very much.
presentation and your face.
Yeah,
The light
you
is
see my
nice.
face. Okay. So microphone positioning. So I can do, this is an experiment that I can do now is, yeah, you know what? Let's try to do it live. We explained, yes, just before, that if I had to measure a speakers, for example, so speakers, even if it's Nexus speakers, doesn't go to 0 Hertz. There is a crossover for the speakers. So let's say that we have, you know what? Let's say that we have something that goes 60 Hertz, so 60 Hertz crossovers. So this is my speakers, okay? And now I take my microphone, I put a microphone on a stand, okay? And this is what I measure, okay? Instead of having my trace, this is what I measure, okay? Once again, what do we see here is comb filtering. And the question is, okay, I have this comb filtering at that positions. That's very strange, okay? What happens if I move a microphone, okay? If I move a microphone and go to a second positions, okay? So I will use microphone, move a microphone and go to a second positions. And going to a second positions, you see that we still have a comb filtering, but what is the difference between the first comb filtering and the other comb filtering? Is the deep of the frequency, they are not the same. Okay, so you know what? Let's try to visualize. I will do a screen captures. So this is my first microphone positions. Okay, I will save the trace. And this is the second microphone positions. Okay, this is the yellow. So the green is the first position and the yellow is the second positions. Okay, so what you see, we still have a comb filtering, yes, but now what we visualize here is we have one impulse that comes 5 milliseconds and the other impulse is coming 10 milliseconds. So what is the reason for that? Any idea? Celso, do you have any idea? Why do I have these things?
But because depending of the distance, you modify the phase, okay? Depending on the length of the reflection, you will modify the phase.
The reflection, the main reflection is a reflection on the ground, okay? So this is something that is well known now. So if I put microphone on a stand, so I will get these first reflections, okay? So what you see in red here is the frequency regions where we have this comb filtering. And when I move a microphone, I've changed the phase relationship. So I have another reflection. And then you see that this part is also affected by the comb filtering, okay? And if I go to a third position, then you see that the comb filtering is quite bigger also again, okay? So going back to my screen again, so there is something that is interesting for us is if we look at the frequency region, there is a part of the frequency region which is not really affected by the comb filtering, that is VHF, okay? Low frequency is very much affected by comb filtering, but not the high frequency, okay? So again, this is something that we can summarize in my screen here. Going back again. So first position, second position, third position, you see that something is keeping consistent. This is this part. So if I want to get rid on this reflection on the ground, so the solution is to get the microphone on the ground, okay? But if I get the microphone on the ground, sometimes I can have this deep also here, okay? So do you have any idea? So this is a PS10 here. We did the measurement with the PS10. And sometimes you can get this one. So what do you see?
A reflection in
yeah, it's not a reflection. It's a yeah, this is a cancellation. And if you look that here, this is exactly the crossover frequency of the speakers. So what we do here, just by having a microphone on the ground, is we have a doublet. So we have a low frequency driver and high frequency driver. And as we are not just in the middle of the driver, we just create this deep. Okay, unfortunately for us, nobody is listening to a speakers on the ground. Okay, this is only
it depends.
it depends. And there is also something which is affected is if we are not on the coverage of the speakers, then you can see a roll-off on the high frequency. So in that position, we can see that high frequency is not accurate, so I cannot really visualize something, but now low frequency becomes very accurate, okay?
Yeah.
So to be honest, if I had to measure something, when I say question and measure your measurement, be proactive, you have to think of what is the microphone positions and what you visualize on your trace, okay? Sometimes there is no possible measurements. This is an example. So this is a top view now. So we said that if we put that microphone right in the middle, but on the ground, we can have a reflection on the side walls. So if we want to get rid of the reflection of the side walls, we can put the microphone on the side walls, but now we have a reflection on the back wall, okay? Finally, the ideal position for that microphone could be to have a microphone on the corner. But is it meaningful just to get a microphone on the corner? Are there any people on the corner? No. Okay. So again, don't be upset if sometimes even if you put the microphone on the ground, you have a reflection. This is real life. Okay. This is not an echoic chamber. We are not in a laboratory. This is live. Okay. And you have to live with that. You have to deal with that. You have to take the decisions. Okay.
But the environment change during the show, with the audience.
Yeah,
it's different
right.
if you have 600 volts or 600 people with long hair. So
yeah, you're absolutely right. So this is why the message is not be careful, because a measurement system is not a computer games. Okay, it's just not by clicking and doing noise and just looking at the trace. It's just really understand what you are measuring, and try also to take the good decisions. Okay, and this is the last example. Sometimes no possible measurement. If you are in a theaters, you cannot get the speakers on the ground because we have chairs, we have many things. So yeah, sometimes you just have to take the measurement tools with you or try to do a measurement, but do not trust 100% what you measure. Maybe trust 20 or 30% of what you're measuring. Right, so let's go to application case, because just look at the time. What is the time? Yeah, so I'm running a little bit late. So let's go to different application. A first application case would be to get this main and delay system time alignment. Okay, so we have a main system, we have a delay system. So I can visualize that. So it's very easy. Once again, I can do it live again. So if I have, let's say that we have one speaker, so no more reflection now. So I will remove any reflections. One speaker is coming in, so it could be this one. Okay, so this is the first one, what you get just before. Again, let's do the time alignments. Okay, great. So this is the very first one. I'm going to do a screen capture on the first one, and now I have a second one. And the second one is coming with a delay. Okay, so let me add the delays. And then it's very easy when I do a screen captures of this one. If I compare the two, that we have one that comes first here, okay, and the second one is coming later. Okay, we have the first impulse, which is here, and the second impulse, which is here. If I play both at the same time, let's do it. Then what you see here, we see the two impulses. Okay, yeah. And I just have to measure the distance between the two impulses. So this is quite easy to manage. So there is a 50 milliseconds. So if I put 50 milliseconds on my processing, let's go 50 first channels, and then it goes, and everything now is absolutely synchronized. Okay, so we have only one peak available here. Okay, so it's very easy, very easy. To be honest, these tools most of the time is extremely convenient, and you are very fast just by measuring the delay. Now it can go a little bit complicated when you have to deal with subwoofer, because when you go with subwoofers, it's quite difficult just to visualize the impulse response. Okay, why it's impossible to visualize the impulse response of a subwoofer? It's because in a subwoofer there is a lot of frequency that are missing. Okay, so the impulse is not very is not very accurate. Okay, you know, let me show you again. If I go to my measurement tools again, okay, so let's visualize, for example, this one, and
the mid-high.
Yeah. So can you see my smart?
Yeah.
Okay,
Perfect.
very great. So I will change it as if it was a subwoofer, for example. So I will go a crossover. Let's do a crossover, for example, at 100 hertz or 120 hertz, and we will cut off at 25. Okay. Right. So let's say that this is not a subwoofer. This is a speaker. Can you see the impulse here?
Yeah.
Fantastic. And now I'm going to go to a subwoofer. So I will cross over at 120. And what you see here is you cannot visualize anything. Okay. If you want to find the impulse, you know, just looking, it's like, well, this is 135. If you find again and find it again, now it's go 35, 38. So it doesn't really know. Okay. It's still changing. And the reasons is because we don't have any impulse. We have nothing. So in that case, the only issue, the only thing that we can do is just to have a look at the phase trace. Okay, so phase trace in that case is very easy just to visualize and to make the time alignment. But remember, when we have to play with the phase trace, we need to take care of this time alignment tools. Okay, so make sure that we do not change it. So what is the good method for that? So this is what we visualize. So this is our sub response. We have a phase response here of a subwoofer. And if we had now the speakers, if the phase is not exactly the same at the crossover point, then what we have here is a cancellation. Okay. So we are not very pleased with that. So the idea now is just to get the delays on the main system and just to make the slope and the phase response of the main system just similar compared to the subsystem. Okay, and thanks to phase linear presets, all the phases are compatible within each speaker and each cabinet. So it's just a matter of playing with the delays. So just adding a delays on both of the subs and the speakers, and you will get this summation here. Okay, so it's very easy to get. Okay, so you know what? Let's put that into practice. I'm going to do like a time alignment between a virtual subwoofer and a virtual speaker. So as you remember, I have a processing. And in that processing, I have one channel, and one channel will be dedicated to main system. So this is currently what we see. So this is channel 2. So we have a crossover point, which is around 120 hertz. And I have exactly the same now with a subwoofer. This is my subwoofer. So we have one main, one subs. And the thing is that we will assume that the subs comes before and the main system comes after. So what I need to do time alignment between subs and main. So currently what we can visualize, if I run both of the systems together, that we can see that in these crossover regions, the overlap between the sub and the main makes not a very good frequency response because the phase between the two speakers are not very good. So I will try to visualize each phase response for each speakers and then try to use the delays of my processing just to get the phase trace as similar as possible at the crossover. So let's start with the main system. So this is the main system. So remember, as we mentioned just before, when you go with the main system, the first thing is just to set properly the time alignment between the measurements and the reference. And I will not do that with the sub for reasons is that it's very difficult, I would say impossible, just to visualize in any impulse response on a low frequency channel. So let's try to do the alignment now. So I'm good. So this is the phase response of the main, and this now value will be kept as a reference. Okay, so I will not change that value again. So let's do a screen captures of the main, and let's visualize now the frequency response and the phase response of the subwoofer. So let's go with the subs, and this is the subs now. So the subs is coming first, and then the main is coming after. So as you can see in the crossover frequency, we don't have really the same phase response. So this is why we have a very bad summation. So now the idea is to get the same phase response. I mean the yellow trace. Try to be as similar as possible as the blue trace at the crossover points. And let's try to go, so I know the value, but let's go 3. So you see 3 as starting to move the frequency response. Let's go 8 now. And 8, okay, so it's starting to be better. Again, increase, manually heat. So this is 10. And I can again play again, just try to increase the value so that the phase trace try to be as similar as possible as the blue one. So currently this is 12 milliseconds. I can go maybe 15. So this is now 15. So 15 is quite better, but maybe I should increase a little bit so that I can get a good matching at the crossover points. Okay, so as you can see at the crossover point, we have matching curves, so they are not exactly the same. Okay, again, we are not measuring any Nexo speakers, so there is no phase compatibility between the main and the sub. So this is a filter, so this is only electronics, but maybe it could be okay just to have this phase relationship between the two. So I will now add the main with the subs, and we can see if we have a summation, and this is the case. So we have a good summation to get.
But remember, you are in front of two possible systematic mistake.
Yeah.
The first one is you. Okay.
Sorry. Say. Yeah, the first one is.
The first one is when you delay the main.
Yeah.
You miss your align with the system. Okay, you're aligned with your measure system.
Yeah.
Okay, you can put the delay for the main, and later maybe you need to redo the finder peak again.
Absolutely,
of the impulse.
Absolutely.
And the other that is very normal, but is people try to pass the phase line, and sometimes need to use the common sense, because many times people know this octave pace, the second octave, and you going back your subwoofer 3.6 meters back. And the line shows that it's good and the sound is terrible.
You're absolutely right. So once again, be careful, because when you play with the phase, because I absolutely understand and absolutely agree with you, we need to be within the cycle. If we have 1 cycle, 2 cycles late, even if we see that the phase rates keep the same, we have 1 or 2 cycle phase, so the sound is different. So the good trick is, with, for example, with the Nexo speakers, we know that there are a line regarding, the phase reference, which is a front grill. So you can start by doing the pre-alignment with a laser, just by having the distance. And just by doing this pre-alignment, you can get your microphone now and at a given position. You need a fine-tuning of the phase, and you can't do any mistakes, because you did that measurement before. Okay, but you're absolutely right.
Thank
you. So yes, once again, when you used to go to the time alignment system, sub, bass, and main, you can go very fast, and you don't have to spend 1 hour just to do that. So be careful of this value when you do the measurements. Application case number 3 would be, for example, if I had to tune any system array. So most of the time what we do when we tune a system is that we have a frequency response at a given positions, but This is not really relevant to get any frequency response at what given positions, because our array is supposed just to get sound for many peoples. Okay, so if we have an audience of 60 meters depth, then we should do many measurements. Okay, for example, if we do one at 10 meters, this will be the second one at 20, the other one at 30. So we see there is a roll-off on VHF due to real absorptions. We also have less low frequency. It's because we are going now into the far field for the low frequency. And then we have many, many curves. So just to mention that the curves that you are just seeing there are just direct sound. So there is no, so this is outdoors measurement. There is no reflections. But if we have also reflections and reverberations coming into that curve, the curves can also be very different from one to the other. So at the end, what you have is a lot of curves, okay? And you have to take the decision. So maybe in that case, the good decisions is to do an average, okay? You average the different positions regarding to different curves, and then you take the decision regarding this average. So you do an average along the depth, but don't forget also to, don't forget that when you also do any measurement, you also have to do average on the width. Okay, so a good way would be just to get different microphone positions along the depth, but also to move the microphone position along the width. Okay, and then you have like a good idea of what could be the transfer functions of your systems along the audience.
Sorry, I received some questions, but I don't know now. Is maybe it's out of the situation. For example, Otto Marquez is asking about what type of window give a better performance. The window, obviously, we are talking about the window time for the measure.
Yeah, so the window time, so once again, the window time is very much related to what kind of software you use. For example, if you use sweep, or if you use any impulse response, when you use any impulse response, then you have to it's a kind of post-production, but you can change the windows time just to get rid on the reflection, for example, or on the reverberation. When you run any dual FFT channels like we use on the software, the software is just managing the time window for you. So we have, I can show you if you want. Let's go back to. This is a very technical question, but let's go on. No worry about that. If we look at the window on the settings here, if I go to here.
Yeah.
Okay, so when you go to transfer function measurement, sorry, where is it? If I take this one. FFT is the window. So there is something which is called MTW, is multi-time window. So what the software is doing for you is taking a long window for the low frequency and small window for the high frequency, because the idea is to get exactly the same number of points in one octave, which is 24. So in that case, I can't change by myself the window. I will be able to do it. For example, I can change if I want. I can go and change the window, for example, but it's not very useful. What the people do most of the time is they deal with this multi-time window options. Okay, so it's a little bit beyond the top of the topics. So if we go, so sorry, I saw the question at the same time. So we have a question regarding overlap crossover.
Yeah.
So which point of phase becomes the reference? It can be anything, and the reasons for that is the phase trace are compatible, so they keep the same. So if you take, for example, 1 point as a reference, if you go 1 octave upper, you will still be good. So as long as you do any overlap, you can take any frequency a little bit before or after the frequency, the crossover frequency. It will not change anything. Okay, with Nexo presets, because they are all phase compatible. Okay. So I still have a couple of things just to explain. So we talk about during any average. Okay, so we have average. And you can use any template for measure response at mixed position. So compare the average to any a template measure response at a mixed position. So it's always good to compare the global picture, so the overall pictures with one single position, which is the mixer, because the mixer is the people who is bothering you just to get the good sounds and so on. So just, yes, to compare, it's great to have a good sound at the mixing position, but it's better if you can have a good sound at every position. Okay, so don't try to promote only the mixer. Try also to leverage all the other people. To be honest, at Nexo, we don't have any templates, any target curves or anything with that. So we just believe, and we strongly believe on the skills of the people. Okay, we are not saying that you should do that or should do that. Okay, it's very much related on the skills and also the kind of application that that the sound engineer or the system engineer is dealing with. And the last application case is this one. Okay. Bring your 48, 24 bits favorite for file, play in the sound and walk around. Okay, enjoy. Never get rid of these things. Even if you have a very sophisticated things on measurements, what do you say? The final cut is your ears. Okay, you play the music that you know, listen to the system before the tuning, after the tuning, and you should get something better. Okay. And that's it.
I have a short question, Nicolas.
Yes.
Prior you depart. Our system is a stereo system, okay?
Yeah.
Our source is a mono source. Our measure system is a mono measure system.
Yeah.
Obviously, if I put my microphone, if I measure one side, I need to measure the other side to calculate the interference in low frequency between one and the other. Okay?
Yeah, but the thing is that you will never be able to get rid of that interferences, because when you go to the low frequency, you're absolutely right. If you run, for example, left and right subwoofer, if I measure the response on the left, if I do a measure on the right, if I play both at the same time, I will not get the same result from my microphone. Okay.
I know. Yeah. It's a topic. This is a question.
Yeah, but the question is, this is how we have to live. We have to live with this one. This is the drawbacks of a stereo. Stereo, when you run any mono signals in a stereo, you get the interferences. Okay, so please don't play both of the system at the same time when you run any measurement, because you will be polluted. But what comes from the other signals, sometimes it's relevant, because when you run, for example, mono signals, it comes exactly from the left and right. But when you have non-correlated signals, like reverbs or stereo things, signals that comes from the left is different, but the signal is coming from the right. Okay, and you have two ears, and so you will not have this kind of interferences. So this is a good question, Celso, also just to make sure that we clearly understand that what we measure is a microphone. Okay, this is a single membrane. We play stereo, sometimes we play 5 channels, more sophisticated also channels, and we have 2 ears. So it's much more complicated than just only having one microphone on a stand at a given positions.
Yeah, we have 2 ears.
Yeah, we have 2
are
ears.
not omnidirectional. Okay.
Absolutely, and they are not omnidirectional. You're absolutely right.
It's a Q8.
Yeah, so. Yeah, you're absolutely right. This is why the last slide. Again, this one. Sorry. This one is fundamental. Okay.
Yeah.
Okay. Check with your ears always. Right. So, do we have any other question coming from the guys? Don't think so.
No.
So just look at the time. It's okay. So I'm just 12 minutes late. So just before we leave, just to mention that we have any. If you have any question, if you have anything, if you need to know a little bit more, we have an email address which is technical@nexo.fr, where all the people from the engineering support. We also have the guys from after sales. So we have many people that can answer questions to anything on that mail. So feel free to use that mail to ask any question. We also have a web link to the cloud. So this is a technical cloud where you can find any information and documentation regarding, specification on speakers, drawings, software downloads, firmware updates, anything. So you can go directly to that cloud. I think there are more information compared to the website. So you can find many things on the website, but you have more things on the cloud. And this is absolutely open to any user. So there is no secrets, nothing. So this is only technical information. Thank you very much. Just have to look if we have other questions here, but I think I'm...
no, there's no more questions.
Yes.
Thank you, Nicolas.
Thank you, Celso.
Thank you too, and it was a pleasure listening in the last hour.
Amazing. So see you next time.
Yes, of course. Thank you, everybody, for coming.
Take care, yes, and everything.
Thank you.
Thank you very much. Thanks, everybody. See you later.